Hey guys, let's take a look at section 7.1 on Achieve. This is a fun section and maybe our second most important section of the semester next to the sections discussing the substitution method. Substitution method is a method that you'll never be able to forget. Probably a close second to that would be the integration by parts that we're doing within this section. Again, just to help the video go a little bit more quickly, I've already answered most of the questions here on Achieve, but I'll be going over how I got each of those answers in detail with you here in the video. So this first problem, we have something like the interval of the group 2x plus 5 times the exponential function e to the x. So what I did in that problem, as you'll see here, is I went ahead and used, I think their advice in this one, they told you to let u equal the 2x plus 5. But what you're supposed to remember in all of these problems is that mnemonic device I talked about in the notes with the liate. So algebra always comes before exponential, a before e, and liate. So we already knew that the 2x plus 5 group had to be our u function anyway. And then the non-algebraic function, the e to the x dx, our exponential function, had to become dv. So we assign u to 2x plus 5, dv to e to the x dx. We take the derivative of u to just get 2 with respect to x, and we integrate the exponential function, and we know that the integral is just e to the x. So then our formula for integration by parts says that it's going to become u times v, which is 2x plus 5 times e to the x, minus the integral of v du. Well, I went ahead and said, well, that's just the integral of 2 e to the x, and I know that the integral of e to the x is e to the x, so the integral of 2 e to the x is still 2 e to the x. So I get my original u times v, that's already part of the answer, and then minus the integral of 2 e to the x, which is 2 e to the x, plus your constant of integration, done. The second problem here on Achieve, I'll go ahead and just keep this open, is the integral of x cubed times the natural log of x with respect to x. So what I did in this problem is, again, I'm thinking liate. The very first letter in liate is L, stands for logarithms. You let u equal the logarithmic function. The algebraic function is going to become your dv. So dv in this problem is x cubed dx. We know we take the derivative of u, that's going to give us 1 over x dx. We integrate the dv, that's the power rule, you'll get x to the 14th over 14. Once you do that, guys, then you can just say, well, our integration by parts formula says to take u times v, so the integral becomes the natural log of x times this. I went ahead and wrote it as what I thought looked more nicely, or more nice, I should say. 1/14 x to the 14th, natural log of x. And I went ahead and put the group around that since Achieve requires that in the final answer. Minus, so it's u times v minus the integral of v du. Well, that integral of v du, I knew it's going to be divided by 14. I just brought the 1 over 14 out in front. Then becomes minus 1/14, the integral of x to the 14th times 1 over x. That gives me the integral of x to the 13th. At that point, you just use the power rule, and you can say, well, that's going to be x to the 14th over 14. So you'll notice that 1 over 14 times 1 over 14 gave me 1 over 96. And I have the terms I already brought out, minus 196 x to the 14th power plus your constant of integration. Pretty cool problem. Up next here, for number 3, we had the integral of the group 10x minus 3 times the exponential function e to the x, and Achieve was asking us again, integrate that with respect to x. Algebraic and exponential, you know you let u equal the algebraic function. So that exponential function e to the negative x dx becomes my dv. I integrate that, and I know that the integral of every exponential function is that exponential function divided by the derivative of its exponent. Well, when I divide by -1, it's the same thing as multiplying by -1. Over here, du is just 10 with respect to x. So now I can say this original integral is u times v. So I said this times this. I wanted to go ahead and put the negative out in front of that group, 10x minus 3, and then times e to the negative x. I thought that looked better. So this is my u times v, and then it would be minus the integral of v du. Well, where did that plus come from? Well, I went ahead and factored out the 10, and I factored out the factor of -1 to make that minus a plus 10 on the integral, and then all I have left is e to the negative x. But you know, when you integrate e to the negative x, you're going to get negative e to the negative x. That's going to take this back to a minus 10 e to the negative x. And then you have your final answer, the portion that was already done, this part that integrated very easily, and then plus your constant of integration. Good stuff. For the next one here, you have an algebraic and an exponential function. So you can say, well, all right, that algebraic function is just to the first power, so taking the derivative once, it's going to really simplify this down and make it a constant. I can say the algebraic function becomes my u, the exponential function always is dv. So then I can say, all right, the derivative of x is just 1 with respect to x. The integral of e to the 7x plus 3, please remember the integral of any exponential function to a linear exponent is always that exponential function divided by the derivative of its exponent. So I can say, well, it's e to the 7x plus 3 times 1/7. Now, when I go to my answer is going to become u times v. I got the 1/7 x exponential function e to the 7x plus 3. And then it's minus the integral of v du. I went ahead and factored out the constant factor of 1/7, and then had my e to the 7x plus 3. At this point, it's similar to the last problem. You can say, well, now I need to integrate that exponential function again. Well, we can. When we do, we're just going to have to divide by 7 again, and that 1/7 is going to become 1/49. You'll have your e to the 7x plus 3. This part was already done and integrated. Plus our constant of integration, you've got your final answer there. Now, one that's going to require a two-step integration. Anytime you have an algebraic times a trigonometric and the algebraic is to a second power, you're going to need to use integration by parts twice. Now watch how it's going to work out in this problem. I let my algebraic function be u, a comes before t, so I know I'll set 7x squared equal to u. The trigonometric function sine of x, d with respect to x, is going to be my dv. So now I can say, well, all right, the derivative of 7x squared is 14x with respect to x. The integral of the sine function is the negative of the cosine function. Okay, so then I can say the integral of 7x squared sine x dx is going to be u times v. It's going to give me a negative 7x squared cosine x. And then it would be minus the integral of v du. And I can say, well, that minus the integral of v du, when I do that, it's going to become plus because of this negative sign. So I get plus 14, and I'll still have an x cosine x on the inside of that. I still have an algebraic times a trigonometric function, but I know I'm in better shape because at least it's a linear times a trig function instead of a quadratic times a trig function. So I use the process again, this integration by parts process again. I can say, well, yet again, let u equal the algebraic function. Du is going to be dx. And so then I can say, well, dv is the cosine of x dx, and the integral of that is going to give me the positive sine function. So now I do that for this second portion. Please notice I tried to show my work really well. The original integral is just the original problem. We already knew it's equal to negative 7x squared cosine of x, but then we had plus 14 times whatever the integral for this part was. Well, we know the integral for that part is going to be x times the sine of x, u times v, that's where that came from, and then minus the integral of v du. Well, that's the integral of the sine of x dx, which we know that's easy to integrate. The integral of the sine function is just going to be the negative of the cosine. When I do that, that's going to change this to a plus. It's going to be plus cosine. And then I distribute the 14 to both of my last two terms, and I get 14x sine x plus 14 cosine x added to what I'd already brought out and the constant of integration for your final answer there. Now, if we move on to a problem like number 6, it gives me the integral of e to the negative x sine x with respect to x. And so I can say, well, all right, I have an exponential and a trigonometric function. This is one of those problems where I immediately need you to recognize it's a cycling problem. It's a problem that we're going to have to solve out algebraically. And the reason you know that is because neither the exponential function nor the trigonometric function simplify when we take the derivative. They just keep on being approximately the same size forever and ever and ever. So I know that this is going to be a cycle problem. I'll use integration by parts 2 times, and I'll have the original question left in my answer, at which point that's an indicator. I just need to move that same integral over to the other side and solve for it algebraically. So in this problem, if I have the integral of e to the negative x sine x dx, I need to set u equal to the trigonometric function. In Liate, t for trigonometric comes before e exponential. So I set u equal to the sine of x. It means everything else is going to be dv, the e to the negative x dx. I take the derivative of sine, cosine of x dx. I integrate e to the negative x to negative e to the negative x. Now, integration by parts says that this is going to be negative e to the negative x times the sine of x. That part is done. It's part of my answer. But then plus the integral of v du. Well, sorry, it'd be minus the integral of v du. The reason it became plus is I factored a negative out. So it is plus once you factor out the negative. And then I have e to the negative x cosine of x dx in there. Now you're looking at this and look at what you originally had. It's no more simple than what you originally had. So you might think integration by parts didn't help. It is going to help. You just have to be patient with it and do integration by parts again. So I have to be very careful and make sure I'll set u equal to the trigonometric term again. Well, du in this case is going to be the negative sine of x dx. If dv is the e to the negative x dx, when I integrate that, yet again, I'll get negative e to the negative x. So now here's the important part. We can say this original problem, that's what we're trying to evaluate the integral of. We already originally found that it was equal to the u times the v, so the negative e to the x sine x, and now it's plus this integral. Well, plus that integral is going to give me, again, u times v, which is going to be minus e to the negative x times the cosine of x. And then you'd say minus the integral of v du. You can say, well, minus the integral of v du, a negative times a negative is going to be a positive in there, so I subtract the integral of e to the negative x sine x dx. Now I look at what I have over here and say, well, that's the exact same integral as this original problem. And you might think that's a horrible thing, but it's a wonderful thing. Because then I can say, well, all I need to do is gather my integrals of e to the negative x sine x dx on the same side and then solve for it algebraically. I know that this is understood to be minus 1 times the integral. I already have a 1 times the integral over here. So if I add the integral to both sides, it's going to eliminate on the right, and I would have twice the integral on the left-hand side is equal to these two terms. And then since we know integration can always differ by some constant factor, I went ahead and put a plus c on this side. Now my final answer is that this integral is equal to everything I have over here divided by 2. Well, when you divide by 2, it's the same thing as multiplying by 1/2. What I did here is I noticed that both of these had a negative e to the negative x as a factor in both terms. So I factored that out, multiplied it by 1/2, and said a good final answer here is negative 1/2 e to the negative x, When you factor that out, you're just going to have the sine of x plus the cosine of x left over. And then, of course, you have plus your constant of integration. Now, for the next problem here, you might say, well, hey, 7 is identical to number 6. It really is. Anytime you have an exponential times a trigonometric function, it's going to cycle around. You're going to have to use integration by parts 2 times and then solve algebraically. This one will be a little bit more fun to solve algebraically. It's not just going to be a 2 out in front of our integral because we have powers inside of my exponential function, unlike last time where it was just the -1 power. Now it's e to the -9x times the sine of x dx. And so I can say, well, okay, yet again, let u equal the trig function. dv is going to be the exponential function times dx. Well, derivative of sine is cosine. The integral of e to the -9x is -1/9 e to the -9x. Then I can say u times v. Well, I'll get my -1/9 e to the -9x times the sine of x. And then it would be minus the integral of v du. I went ahead and put plus 1/9 factored out, and I have e to the -9x times the cosine of x dx in there. Once again, just like last time, I can say, well, this is every bit as complicated as this is, but if I just be patient and use integration by parts one more time, I'll be able to solve algebraically. So I do that. Set u equal to the trig function. dv equal to the e to the -9x dx. Derivative of cosine is negative sine of x dx. The integral of e to the -9x is e to the -9x divided by -9, which is better written as -1/9 e to the -9x. So now I need to go in here and say, all right, my original problem right here, I already knew it was equal to u times v, the original u times v. I've already done that. But then I knew it was plus 1/9 whatever I get for the answer of this interval. I'm trying to show my work here well, so I said plus 1/9 times the group. Now what's inside of this group? Well, it's the integral of this, which is what? Well, it's u times v. That's the -1/9 e to the -9x times the cosine of x. uv minus the integral of v du. Well, minus the integral, I knew the negative times the negative, both of those terms are going to be positive on the inside. I factored out the 1/9, and I get my e to the -9x sine x dx inside that integral. Once again, just like number 6, I recognize the integral that I have on the right-hand side is the same as the integral I have on the left-hand side. But now I need to be very careful here. I also recognize that it has a coefficient of -1/9 times 1/9 in front of it. So that's 1/81, or negative 1/81 multiplying that integral on the right-hand side. So then you need to say, well, then you need to add 1/81 times that integral on both sides. That's what I did right here. I already had 1, which is understood to be 81/81, plus 1/81. I had to add that to both sides to get rid of the integral on the right-hand side. And I've got 82/81 times that integral on the left. Now, the only two remaining terms on the right-hand side, because the whole point in doing this was to get rid of that term right here, get it on the same side, I'll have these two. I just bring them down, add the constant of integration, because again, I know whenever you integrate, it's always plus or minus some constant of integration. So as soon as I get the integral to one side, you really do need to add a c to the other side. And now, in order to get to your final answer, you just say, well, just multiply both sides by 81/82. And that's all I've done here. Now, when I multiplied by the 81/82, what I did here, that multiplying by 81/82, I simplified out and I factored out the -1/82 because I noticed I could factor out a -1/81 e to the -9x out of both of these terms. When I factor a negative 1 over 81 out of the first term, it's going to leave me a factor of 9. The factor of negative 1 over 81 out of the second term, it's going to leave me a factor of 1. So you've got your 1 cosine. I factored that negative 1 over 81 out, multiplied it by 81 over 82 to get my negative 1 over 82 there. So just some arithmetic that I did from this step to this step. Now, do you need to factor and simplify like I did? Nah, you don't need to, but I think it's cool to. You could have just left your answer as this times 81 over 82, and that would be fine. For the next one here, you can see it's a pretty short problem, number 8. We have the integral of x to the 4th times the natural log of x with respect to x. So I can say, well, okay, in order to integrate this problem, I'll let u equal the natural log function. Then dv is my algebraic function, the x to the 4th dx. Well, derivative of natural log of x is 1 over x dx. The integral of x to the 4th, x to the 5th over 5. So then our answer, and this is a really quick one, we get u times v, natural log of x times 1/5 x to the 5th. I called 1/5 x to the 5th, natural log of x, minus the integral of v du. I went ahead and factored out the 1/5. X to the 5th times 1 over x gave me the integral of x to the 4th. Whenever you integrate that, you're going to get x to the 5th over 5. Well, that over 5 multiplies the 1/5 out in front to give you minus 1/25 x to the 5th for that second term. Plus your constant of integration, you'd be done with the gorgeous number 8. A couple more problems here. If we look at number 9, and there's really no need for me to show the achieve page because it's just a listing of these problems. So I'd have to go back to my work anyway. But the answers I've circled here are the answers that I inputted into achieve. For number 9, we have the integral of the natural log of 19x quantity squared, and we're asked to integrate that with respect to x. Okay, so you really don't have a choice for what to set u equal to. It's the entire natural log of 19x quantity squared. That's the only term in here. And then dv, again, you really have no choice. It has to be dx. So now you have to take the derivative of this group to a power. So you'll say, all right, derivative of any group to a power. This is a good review of the Calc 1 chain rule. You bring the 2 down in front of the group times the group to the first power times the derivative of what's inside the group. Well, we know the derivative of the natural log of 19x would be 1 over 19x times 19. That multiplication of 19 and the 19 in the denominator canceled to just give you the times 1 over x there. And all of this is the derivative taken with respect to x. On the other side, you integrate 1 with respect to x and you get an x. So the integral of 1 is x. So now when I try to simplify this, I can say, well, my original problem is u times v, x times the group squared, minus v du. You say, okay, when I multiply v times this du, this x and 1 over x are going to eliminate one another. I'll have this 2 brought out in front of the integral, and then I'll have the integral of the natural log of 19x dx left over. What I have left inside the integral is better and easier to simplify than what I had initially. So I'll go ahead and use integration by parts again. I know that integration by parts is helpful in this problem, but one application was not enough. So yet again, I let u equal the natural log of 19x, and then du is going to be 1 over 19x times 19, which simplifies to just 1 over x with respect to x. Your dv in the problem, yet again, is dx, and v is going to integrate to x. So the original problem is the original u times v that I got, and then we had minus 2 times the group, where I had to integrate again. Well, that was the u times v, the x natural log of 19x, minus the integral of v du, which is just minus the integral now of 1. And then du is my 1 over x dx. With the 1 over x part canceled out, I'm just left with 1 dx in there. Well, I know that the integral of 1 with respect to x is just x. So now my final answer, this takes part of it. My second part is going to be minus 2x, natural log of 19x. Please don't forget to distribute that negative 2 to both terms. I know when I integrate a 1, like I said, it's an x, but it's going to be a negative 2 times a negative 1. That's going to be a plus 2x. Now, I almost forgot to put my 2 in there on that term. I scrunched it in. And then, of course, plus your constant of integration. For the next problem here, I absolutely love integration by parts for inverse trig functions. Let's integrate the inverse cosine function together. So if we have, like in number 10 here, the integral of the inverse cosine of 2x with respect to x. Well, all right. Again, just like the last problem, there's no choice of what to let u equal. Let it equal the entire inverse cosine function. Then dv has to be dx. The integral of 1 dx is x. Please remember from Calc 1, the derivative of the inverse cosine is the same thing as the derivative of the inverse sine, it's just the negative of it. So I get a negative 1 over the square root of 1 minus the group 2x quantity squared. I went ahead and wrote as 4x squared. Normally, if you show all of your steps, you'd say negative 1 over the square root of 1 minus the group 2x quantity squared times the derivative of what's on the inside. Well, that's a 2. So now I can go ahead and say, well, of course, that derivative is with respect to x. When I go back to my problem now, I can say then this integral is equal to u times v, x inverse cosine of x. And then it would be minus the integral of v du. Well, minus the integral of a term that's going to have a negative on the inside. I went ahead and put a plus on the outside. I also went ahead and brought out the factor of 2. Then I would have the integral, and you can ignore the red part just for a second. Then I would have the integral of x goes into my numerator, and then my denominator becomes the square root of 1 minus 4x squared. Of course, all integrated with respect to x. Now, at this part of the problem, as soon as I saw the fraction in there, I was pretty certain integration by parts was not going to be helpful anymore. So instead, I'd rather use substitution because that's also not something I can go ahead and integrate with simple techniques. So substitution, you can say, well, normally you let whatever's inside of a group to a power be the substitution variable. I've already assigned u earlier in the problem, so I'm going to use a t substitution. And I'll set t equal to what's inside the square root, the 1 minus 4x squared here. All right. Well, if I do that, the only way I can do that substitution is if I can get a dt in the problem. Well, if t is 1 minus 4x squared, then dt has to be negative 8x dx. I didn't see a negative 8x dx in the problem, so this is where I showed in red, well, I can easily multiply by a factor of negative 8 on the inside in order to allow this substitution. But in order to do that, you have to divide by a negative 8 on the outside. So the outside becomes 2 times negative 1/8. And the next step, you'll see that's where I got the minus 1/4. And then my integral, remember that negative 8x dx all becomes dt. So you just have 1 over the square root of t dt. Well, 1 over the square root of t is better written as t to the 1/2 power. At this point, I can say, man, now I can just integrate with the power rule. So my original integral, which is this right here, is equal to the u times v, the x inverse cosine of 2x. And then this last group simplifies to just become t to the 1/2 power divided by 1/2, which means times 2. So I have 1/4 times 2t to the 1/2 plus my constant of integration. Well, the 1/4 times 2, that's going to be minus 1/2. And then I know t is nothing more than the group 1 minus 4x squared. So I can say, well, then I have minus 1/2 times the group 1 minus 4x squared raised to the 1/2 power plus c. Now, normally I would rather go ahead and put it back in terms of square roots, but with this being achieved, I recommend the fractional exponents instead of roots. They tend to be more accepting of answers to fractional exponents. Oftentimes they'll accept both, but if it's one or the other, they're going to want the fractional exponents, unfortunately. So it's probably better to leave it like that. For the next question, and this will be the last one I'll look at in this video, and then I'll finish up this assignment on another video. For number 11 here, we have the integral of an exponential function times a trigonometric function integrated with respect to x. So in this one, I went ahead and I set u equal to the exponential function. It really doesn't matter. Most of the time, I probably would have set u equal to the trigonometric function if you strictly follow Liotte. In this case, it doesn't matter. I knew that 5 to the x was really easy to take the derivative of, so either way, it's going to work pretty easily. I said, let's let u equal that 5 to the x. Then du, derivative of any exponential function, is that exponential function times the derivative of its exponent, which is 1, times the natural log of its base with respect to x. The integral of the cosine function is going to be the sine function. I get the sine of x there. So now, whenever I try to work this out, I can say, well, then my original integral is going to integrate to u times v, 5 to the x sine of x, minus the integral of v du. Well, that's going to be this function times this function. I'll have the natural log of 5 brought to the outside, and I'm still going to have that 5 to the x sine of x dx in there. I knew, just like a couple of problems earlier on, that anytime you have an exponential and a trigonometric function in there, it's going to be a cycling problem where you're going to have to solve algebraically. So it's really irrelevant whether you set u equal to the algebraic or the trigonometric function, but whatever you choose here, you need to be consistent with that choice. So I certainly wouldn't want to set u equal to the sine function now, or else it's going to undo the work that I've done. So I'll say, okay, then let's let u equal the exponential function 5 to the x. Yet again, du is 5 to the x, natural log of 5 dx. This time dv is the sine of x dx. The integral of that is going to take me backwards to the negative cosine function. So now I can say, well, then the original problem was my original answer, u times v, 5 to the x sine of x, minus the natural log of 5 times the answer I got for this second integral, which again is u times v. That's a negative 5 to the x times the cosine function. And then it would be minus the integral of v du. Well, you notice I went ahead and put a plus because I factored that negative out, and I also factored out the factor of the natural log of 5. And when you do that, you'll have the integral of 5 to the x cosine of x dx left in there. As soon as I get to that point, I can say, that's the same thing as the integral on the left-hand side. Okay, then what would be the coefficient of this integral of 5 to the x cosine x dx on the right? And you've got to see you have a negative natural log of 5 times a natural log of 5 multiplying this integral on the right-hand side. So I can say, well, okay, that's a negative, the group natural log of 5 quantity squared multiplying that. Then I need to add the natural log of 5 quantity squared to both sides. I did that. That's what happened from here to here. You've got to understand, I already had an understood coefficient of 1 in front of it on this side. Well, 1 plus the natural log of 5 quantity squared, when I move this to the same side, gives me this as the coefficient. And no, you do not want to put that as a decimal. We want exact answers. So I have 1 plus the natural log of 5 quantity squared times the integral of the original problem, 5 to the x cosine of x dx. It's equal to my u times v that I originally had, minus the natural log of 5 times this term. So I have minus times a negative, that gave me plus 5 to the x natural log of 5 cosine of x. And then whenever you get your integral all on one side, you do need to put plus the constant of integration. Now, my final answer, well, it's all of this divided by this 1 plus the natural log of 5 quantity squared, and then you can stick your constant of integration at the end. And please notice that format worked out gorgeously for the answer that Achieve wanted. That's exactly how I typed it into Achieve, and Achieve was really happy with that answer. Okay, guys, hopefully this gets you confident with the problems in this, or at least the beginning problems here in this section 7.1. There's some pretty important topics in this section. Please let me know if you have any questions. I'll be glad to help. These are some fun problems. I look forward to doing the rest of them in the part 2, covering questions 12 through 18.